All right, everybody. So here I've got you can kind of see that I've got a measuring tape measure. And then attached to that is a spring, or not attached to it. Up here, this is like a little thing with a spring on it. I'll show you that on the camera, right? If I go up, see that? There's a spring right there, okay? And what I'm going to do is I'm going to hang some masses on this thing, and I'm going to try and record how far this thing goes down, right? But I'm going to probably just keep the camera down like this without really moving it too much because it ends up getting a bit fiddly if I move it around. Okay. So anyway, there I've got that. And then over here, you can see that I've got a graph. Okay. And what I'm going to do is in this graph, I'm going to plot some points here. Okay. And here I've got 0 and 0, 0, 0. I'm going to hang 4 different masses on here. And in these locations, these zeros here, I'm going to write the kilograms that I hang on it. And then I'm going to write meters. I'm going to write the distance that the thing ends up moving down, right? And I'll calculate, and I'll see that all here. And so I'll go ahead and I'll type all that information in as it unfolds, and we're going to keep track of these points here, okay, as we kind of go through. All right. So what I'm going to do is I'm going to take 100 grams, it's this one here, and I'm going to hang it onto here, right? And so you might not be able to see it perfectly, but we're just going to do our best here. And basically with 100 grams, I was able to, it looks like I'm getting about a 12 millimeters, okay? It's about 12 millimeters. It goes in right around there, okay? And so what I'm going to do is I'm going to write 100 grams. Oh, but that's in kilograms. So I'm going to write 0.1, and then I'm going to get 12 millimeters. So that would be 0.012 right in there. And there, that red point ended up moving to there. Okay. Now what I'm going to do is I'm going to add in another, 100 grams. Okay. So I've got another 100 grams here. Okay. And I'm going to go ahead and hang that on there. And there we go. Oh, there it goes down there. And I'll go ahead and point my little thing there. It looks like we're getting around 20. Oh, I don't know. I'm going with about 24. Okay. Maybe 23. It's not easy, right? You can kind of see that thing, I'm focusing on the bottom of that hook right there. And it's right there around 24. You can kind of see it. It's not easy to see, but my lighting is a bit off. So that's 24, and that would be 200 grams. And so you see how I've got 0.2 kilograms and 24.024 millimeters. All right. Now I'm going to do 300 grams, and we're going to see how far that one goes. So 300 grams is going to be another one of these guys. This is another 100 grams. And there we go. I'll go ahead and hang that guy on there. And sure enough, we're getting to right around here. I'm going with about 36. It looks like to be about 36. That's 35. That's 36 millimeters. So I'm going to go with 36. Okay. Now, I actually don't have any hundreds left, but I have a 50 here. And so I'll go ahead and hang this 50 on there. All right. And we'll see what we get there. We're going to hang that 50 on there. Oop, everything moved a little bit, but that's okay. We're going to see what we've got. I'm looking at this and I'm seeing personally about, let's see. Oh, I lost my mouse cursor. There it is. I'm seeing about a 41. You see that? I'm going with maybe 41 on that. So that would be 350 grams. So I'm going to write a 350 grams. And I'm going with a 41. Okay. So 41. So there you go. All of our points ended up showing up on this graph. And if you look closely at them, look at that. They actually show up in a pretty nice flat line there, okay? And so what we want to do is obviously we definitely have a pattern here. And this pattern looks very linear. Okay. And so the fact that it's a linear situation is quite evident. All right. And so what I've done here is I've produced an equation. And it's this black line here. F force is equal to kx, right? And this is the form of a linear equation. If you look closely at it, it's like y equals slope x, and right. So right now I've got the k value set to 0. Okay, and what I'm going to do is here I've got this little slider here, and what this slider does, it allows me to move. You can kind of see my line moves up, and I'm going to try and look at that right there. As soon as I hit point 12, right, or 0.012, I've basically achieved, I've kind of mimicked the pattern of these lines here, or these points, with this formula, in the case that 0.012 is my k value. Okay. Basically, what I've done here is I've reproduced a scenario where we were able to, in a way, build what is known as Hooke's law. Okay, so I'll kind of pull up a little document here, and here it is. It's Hooke's law, right? Hooke's law says that the force applied on the end of a spring should always equal kx, and this is a linear equation. Like, he didn't put x squared here, Mr. Hooke, or he didn't put the square root of x, right? He put a kx because he noticed that as this all happened, it was linear, right? And so here this is defined as force applied to the end of the spring, and it's in newtons, okay? And the distance that the spring stretches or compresses, all right? In this case, we used a stretching spring, but it also works for compressing springs as well. For example, the kind that are on your car. And then also here we've got K. This is sometimes called the force constant, right? And it's for the spring being used, all right? Note that this is a characteristic of the spring, and it basically it travels along with this spring. And unless the spring becomes damaged or destroyed, that K value will always be the same, right? And its units are newtons per meter. And so for this particular spring that I have, the K value is 0.012, and that's newtons per meter. Okay. And so there you have it. That's a little bit of info on Hooke's law.